Ah, you know, in this hobby of ours, it's hard to know sometimes if something, a particular experience, is gratifying or annoying. It feels annoying, but I kind of know it's gratifying in some way. You know, on the one hand, it must be, and on the other hand, I kind of see how, because these things, these answers, you give people answers, they're so clear. I don't doubt them. They just, there it is. And the best of you still will stick with some old canard. And I'm thinking about quantum mechanics and this the guy that made the video that Professor Anton replied to, that I then have replied to, which, he says there's no randomness. And then I'm talking with the guy in comments about quantum mechanics, and I'll spare you the details. But the same old canards come up against quantum mechanics time and time again. One, what about the macroscopic effects? I don't know if it really counts on the macroscopic level. Okay, we'll get to that in a second. And then the other one, it's just the general idea of randomness and not getting randomness. And that I understand actually. Randomness is, I do remember how hard it is to get a hold of the concept of randomness and discriminate between different kinds of randomness, just like it is for infinity. The infinity is hard enough to get. We talk about, can people really fathom it? Well, one way they could fathom it that they show trouble with is just that there's different, sort of shapes or sizes of infinity. Not all infinities are equal. Some infinities have more in them than other infinities. You know what? Yeah, well, a line segment has an infinite number of points, but a plane segment, has two-dimensional infinite number of points. So there you go. And the line segment is a part of the plane segment, so obviously there's infinite number of line segments, so there's this whole moreness of it. Okay, anyway. But even with the problems of randomness, I mean, it seems like that one, okay, is easier to understand. People go back and back and back about it, but the first one about the macroscopic effects drives me nuts. Okay, do you guys know what kind of effects are quantum effects? Here, the fact that one material thing can just travel through another material thing, right? Two material things, and instead of bumping into each other, one just travels through the other. Okay, that's a quantum kind of effect. So, for example, crystals. That light goes through the crystal. It's a fucking rock. What is the light doing going through it? Okay, or glass. And that's the thing about the macroscopic effects too. Is like, okay, magnetism. I told this to people so many times. I use this example, and to me, I don't see how it's not the simplest thing to understand in the world. This answers your thing about macroscopic effects. Okay, magnets. Every atom, everything around you is a magnet. But you don't see a lot of magnets. Things don't do that magnet thing, do they? No. Why is it? Because the magnets in these atoms are all at different angles. So that, one magnet is down with one next to it that's up. Or, no, that would be kind of not very likely either. So they're just at random. But since there's millions of them at random things, the law of statistics says they're pointed in all directions evenly. You get very low magnetic uh, fields off of things, and yet they're all made of magnets. You see, so at the microscopic level, everything magnetic. All the particles are moving around; they're reacting to local magnetics. In macroscope, you don't see it. It's not because the effect doesn't work. It's not because it doesn't apply to the macroscope. It's because everything is a random orientation. So in that orientation, it cancels out. Every once in a while, you find a magnetic material. In nature, you discover magnets, and then you can even make them. And then you make them for pennies, and you give them to your kids, and they're all the hell over the place. Okay, quantum mechanics. What about glass? It's solid. It's silicon. It's solid. Light goes right through it like it was nothing. It's a quantum effect. We mastered it. Okay. Now, we just did that one by luck because that quantum effect is fairly common at the macroscope compared to some of the weirder ones. But we're exploiting the weirder ones now too. Because all you have to do is line the effect up. Okay, it's a metaphor in this case, but it's a very good metaphor. Magnets, you got to line them up so the north is on the north, and you put them next to each other, and you do that with millions of them, and the whole thing becomes a magnet, right? Quantum mechanics, same thing, line the things up. The randomness issue, people are confused. Various things. One thing they're confused about is that it's just random because we can't predict it. No, that's classical randomness. Quantum randomness is different. Okay, it's different. Okay. Now, they think that quantum mechanics, the randomness and the spontaneity means there is no cause. No, there is a cause. It's just that one cause can have five effects. Which one happens is random. Doesn't mean anything can happen. Some things can't happen from another particular thing. But more than one thing can happen, and it's random which happens. That's the idea. Now, in quantum mechanics, you could rectify it. The Copenhagen, I don't know, I don't want to call it classical, but this first dominant interpretation of quantum mechanics, definitely randomness. Because who knows? Supposedly there's all these possibilities, and it collapses to the one we see. We say that because we see it, so it must happen. So, and why? That's random. Okay, but the many history ones, well, less random there because that says everything happens. Okay, but does that happen at the macroscope? Well, nobody's ever proved or seen anything to say that it happens at the macroscope. You see it at the quantum level, at the particle, at the photon level, for example, but doesn't it cancel out at our level, right? So for us to be doing many histories, so even if the particles explain that, they're doing everything. So it's deterministic again, you see, right? One cause has these multiple effects, but all of the effects happen, so they can be considered, a complex effect. And you get determinism back. But the problem is it's still random. Why do we only see one of them? Why does it collapse down one way? Okay. So then, you have you know, the, the the science fiction version of, well, because there's multiple universes. And actually on the macroscope, we split and do all the things too. But then it's still random. Why do we feel this way and not the other way? We split and went on all of them. We only feel this one. Why do we only feel one and why this one? So the final unification we can do right now, there's new unifications for the future, but is that we are in all of those. And we do feel them all. We're in all. There's a 100% chance we'd be here because we're in all of them. Okay. And but the laws of physics are such that it's like tentacles. We have one multidimensional body, but each body in one of these time spaces is like a tentacle that it doesn't have nerve connections to the other parts. Okay. But are we willing to accept that, as, that we did all of that to get back to determinism? Now we're this multi-dimensional creature, and we got our determinism back, but I don't know if we've made things less fantastic sounding, right? Because it is possible just to say, it looked like there was randomness way back. Then we thought, no, it's all that ordered because we got it more and more ordered. Then we got it so ordered we found out, no, there's randomness down there at the bottom. We could just accept that. Okay, it's been a long quest, But if we really want, I'm in the multi-dimensional thing. I like it. Let's go for it. But I mean, if it's to redeem a common sense version of natural philosophy, that won't work. It's just like the hidden variable things. Those attempts to make a deterministic interpretation. It's technically deterministic, but it's weirder than hell. The hidden variable theories, most of them have failed, but the ones that still, haven't been proven inaccurate, they involve all kinds of weird things. Time, photons flowing back through time and stuff. So, I mean, it could be true, but it's not like it saves you from the fact that now your physics is fantastic.